Hello, my name is Alexander Cowtan, and I'm going to be talking about parallel logical measurements via quantum code surgery. I apologize for not being able to be present in person at the conference. I hope it's very good fun. This work was done with Sunny He, Dom Williamson, and Ted Yoder, so I'd like to thank them as well. And the aim of this work is to think about how one can compute efficiently and fault tolerantly using large, kind of generic high rate LDPC codes. So going through these adjectives, by large, I really mean large enough that one can't do kind of extractor slash tour de grosse style schemes of um, logical measurements, which have relatively low space overheads, but necessitate some amount of serialization of logical measurements, and therefore are maybe not so good once you get to higher rate codes. And by generic, I mean that the LDPC codes are not presumed to have any nice transversal gates or automorphisms or similar such properties which allow for massively reduced space overheads for computation. And the setting for this work is going to be primarily in the asymptotic regime, and I'm going to, just for simplicity, assume that we can toggle and modify the connectivity between qubits without issue. Um, Actually, some of this scheme can work in a fixed connectivity setting, but this gets quite a bit more complicated, and so I'm just going to omit that. And as far as the asymptotic regime goes, obviously, if the only thing that you cared about was the asymptotic regime, then you would do some kind of Gottesman style gate teleportation protocols using good LDPC codes. But even though this work will not give you constant overhead in general, we argue that the asymptotics kind of inform what sorts of protocols might be feasible at greater than, say, the size of the gross code or the two gross code, but less than however many millions or billions of qubits you need in order to make gate teleportation viable. And with that in mind, the main result of this work is that for any qubit stabilizer code, we can measure any collection of logically disjoint Pauli product operators, that is, Pauli product operators whose terms do not overlap, on T logical qubits using up to polylog factors T, omega, and qubits, where omega is the maximal weight of the representatives of the Pauli logicals contained in the Pauli products. So unpacking this a little bit, this kind of requires choosing a logical basis for the code, and so the kind of max weight of the representatives will be something which is determined by that choice of basis. And so also is kind of the nature of what it means to be logically disjoint. And this kind of set of measurements that you're doing is all done in time O of d, where d is the distance of the code, which is independent of the number of qubits that you're measuring at the same time, and so it is genuinely kind of parallel. The terms and conditions that apply are basically to do with what this scaling of the omega is compared to the size of the code, which is a detail which I'll get to later on. So in other words, given some arbitrary quantum LDPC code, you can run these kinds of logical circuits where you have Pauli product measurements performed in logical time steps, and you're performing each of these logical time steps genuinely at the same time. So my XZ and my ZX measurement are being done at the same time, and then the next step, and so on. Actually, you can use the same scheme to also do measurements which are slightly more general than this, but again, that gets a bit more complicated, so I'll leave that out for now. And the scheme that we're going to use to to perform these parallel logical measurements is going to be quantum code surgery. And the kind of prototypical type of quantum code surgery is lattice surgery with surface codes. And in this case, you can, I have some diagram of lattice surgery on the top right, where we're doing some kind of merge to give me an X tensor X measurement and then a split to retrieve the initial code blocks back out again. And you can always think of lattice surgery with surface codes in this way, but actually it's better to think about it in terms of more atomized generators where you can do the merges and the splits and other sorts of similar operations kind of independently of one another, which allows you to build things like CNOTs and many other kinds of gates and protocols. And I have some kind of diagram of a logical block style CNOT in this kind of Google SketchUp-esque manner that was popularized by Austin Fowler and Craig Gidney. And surgery with LAPC codes is a bit different because essentially reasoning about doing splits and merges independently and how they affect the rates of your code and all that kind of thing not only gets very complicated, but is quite often kind of inefficient. And so surgery with LDPC codes focuses mostly on the logical measurements themselves, and these can be described using so-called scalable tanagraphs. So in the top right here, I have a tanagraph for a Shor code, 913 code. And in the bottom left, I have a kind of scalable tanagraph for an arbitrary CSS code. And here we have a collection of data qubits, which is associated with a vertex. And we have a collection of X checks and a collection of Z checks. And each edge is annotated with a matrix over F2, where the matrix is given by the restriction and lift to data qubits and checks respectively of the stabilizer matrix of the code. So here, kind of trivially, the matrix is the Z check matrix of the entire CSS code, and the same for the X check matrix on the left-hand side. And you can use these to build up kind of diagrams of more complicated codes or deformed codes. And so on the right-hand side here, I have a scalable tanagraph for a hypergraph product code, where I have some classical code with parity check matrix del1 that I've started off with, and then I've tensored that or taken the hypergraph product with a another classical code, which is the repetition code with block length 2, and that gives me this kind of diagram on the right-hand side. And you can kind of check by tracing around the different parity check matrices that this does indeed commute as a code. And you can kind of think of this as essentially a commuting diagram in category theoretic terms. An important kind of building block for our scheme is the gauging logical measurements framework, which starts off with some logical operator. Let's say, for convenience, a Z logical operator in a CSS code, although it doesn't have to be. And then introduces new qubits and checks in order to measure that Z logical operator in a way which is fault tolerant and maintains the LDPC property and so on. And so one introduces a new set of Z checks which are associated with a set of vertices in an expander graph, and a new set of qubits as well, connected to all of the incident X checks to my Z logical that I started off with. And then I also need to have some new X checks which are gauging the cycles of this expander graph, which essentially are present in order to make sure that no new logical qubits with low weight representatives get introduced during my scheme. So I'm going to start off with my code on the left-hand side, so ignoring everything from the M and F matrices onwards. And then I'm going to initialize this new deformed code where all of the ancilla qubits that I need for this, my edges here are going to be initialized in plus for Z logical measurement. And then I'm going to measure for D rounds, and then I'm going to measure out again afterwards in the X bases. And this performs a Z logical measurement. And this is kind of comes from or is very similar to the kind of check weight reduction schemes of Hastings from a few years ago now. And it's nice in kind of a few ways. So first of all, for measuring a single logical representative, it has very asymptotically low overhead, requiring almost linear new space overhead in terms of the weight of the representative which was being measured. It doesn't introduce any new logical qubits, so we don't need to worry about that. And it also provably preserves the fault distance if you run it for D rounds. And despite this, I mean, there might be other drawbacks as well, but the one that I want to focus on here is the fact that if you have a single expander graph, then you can only measure one logical operator at a time using it. So what I mean by this is that if I go to clean my Z logical operator here into the new qubits of my code, then the way that this should work is that it should clean to 0 over here. So if I multiply through by some of these Z checks, I mean in this case all of these Z checks, then I should end up with no new Z support on these instant qubits. And therefore, my Z logical operator has been converted into a stabilizer in my deformed code. Essentially because every simply connected graph has the kernel of the instance matrix of that graph from vertices to edges has dimension 1, you can only measure one logical operator in this way at the same time. And you can check that loosening this a bit to make it just connected but not simply connected doesn't help for other reasons. And what you might instead want to do is just make kind of disconnected expander graphs, each of which measuring some logical operator. But this is going to give you some pretty big problems in a high-rate code because the representatives which you might want to measure are going to overlap substantially with one another. And this gives you two problems. Firstly, and most importantly, you might lose the LDPC property. And in fact, if it's a high-rate code, then if you just glue these expander graphs in this manner, going to lose the LDPC property. And secondly, depending on how you initialize the new checks and what the connections are, the checks in the deformed code may not even commute with each other. So if you have some X logical operator which overlaps but commutes with a Z logical operator, then the new checks which you initialize to measure these may not commute with each other. This is relatively easy to solve, but number 1 is a bit trickier. And so we're going to use two different approaches which are going to combine together to give us something which solves both of these problems. And the first technique we're going to use is what's called brute force branching. And the second technique is a specific choice of logical basis for our LDPC code such that we can guarantee that we can actually measure all of these things in parallel without introducing any anti-commuting checks or anything like that. So with brute force branching, one starts off with, say we have all of our logical representatives over here, and say that we want to measure some of these, say the pink one, the yellow one, and the blue one. Then brute force branching essentially works by trying to introduce new ancilla qubits in order to split up the supports of these representatives in such a way that they're disjoint so that one can then measure them afterwards without blowing up your LDPC property. So if I have T of these logical representatives that I want to measure, and each of them has at most weight omega, then it's going to cost me log t times this t omega in order to branch these representatives out. And the reason for this is because if I start off with my um, logical representatives that I want to branch here, and then I start doing these branches, I'm going to say that I'm going to make a binary tree. It doesn't have to be binary, but for the sake of argument, let's say it's binary. Then at every round, I'm going to essentially split my number of logical representatives in two, and then keep branching until each representative is represented by a single leaf of my binary tree. And the depth of this binary tree is going to be log t asymptotically, and the kind of size of each layer of my binary tree is going to be at most O of t omega, where the biggest layer is going to be the last one, where all of them are split up onto leaves. And the structure of this kind of brute force branching scheme is going to be made using the hypergraph products, like I showed at the start with scalable tanographs, where we start off with some now set of z-logical operators, and then introduce new hypergraph products, which move the support or add equivalent support to split these up and keep going until you have all of these on separate leaves. And you can prove that this always preserves the LDPC property, and that introducing these branches does not reduce the fault distance or anything like that. And adding this kind of log t factor in order to branch everything seems kind of fine asymptotically. Log t is not that bad. But the problem is that the constant factors are pretty brutal. So if I have my logical operators representing some reasonably large portion of my code, then each layer could be kind of approximately the same size as most of my code. In which case, I really can't afford to do this for very small codes. It's only kind of feasible once the LDPC codes are high rate and efficient enough that this sort of scaling is manageable. And I'm going to elide the details of how one then goes from doing branching on z-logical operators to branching on a combination of z, x, and y logical operators. But essentially, the scheme requires certain conditions on the supports of my representatives, which I'm going to branch. And it turns out that every qubit stabilizer code has a logical basis such that there are representatives for every logical qubit which satisfy those conditions, assuming that you're trying to branch representatives which are acting on different logical qubits. And in fact, what's kind of nice is that this choice of basis is precisely the standard form which Gottesman put in his thesis kind of 25 years ago or whatever. And the main caveat to this kind of choice of logical basis, which guarantees that you can always branch in this manner, is that I have this kind of omega factor in my asymptotic scaling, and this omega, while one would like it to be close to d, the distance of my code, it can in fact be much higher, and because this standard form is obtained kind of essentially by Gaussian elimination, the representatives can have weight which scales with the size of my code, not just the distance of my code. Now, this is fairly unavoidable in a certain sense if you're dealing with generic stabilizer codes which you don't know anything about, because even if they have a much lower distance than the block length, finding low weight representatives, if they even exist for every logical qubit, is going to be extremely hard in general. And so this kind of caveat is kind of inbuilt to the nature of doing surgery in this manner. Okay, so now I've shown that you can branch out from the original code and preserve the LDPC property by having all of these representatives on leaves. And then you can measure single qubit logical Pauli's using the gauging logical measurements framework that I showed earlier. If you want to measure products of these Pauli's, then there are ways that you can apply the gauging logical measurements protocol kind of verbatim, but instead we're going to use universal adapters because it slightly improves the overhead. So on the left-hand side here, I have an example of, say we have some code to the left that's kind of indicated by ellipses with some Z logical in that code and its incident X checks, and then we have kind of the same thing on the right-hand side. Then each of my new expander graphs is given by this kind of column through the diagram here, and the same on the right-hand side. And it turns out that you can provably always construct a small set of checks and qubits which connect these up in such a way that rather than measuring single logical qubits, you instead measure products thereof. And this doesn't add any asymptotic overhead to the scheme and always preserves the LDPC property. And here I've just shown how one might measure, say, a two-body logical operator. But you can chain these together in order to measure higher weight Pauli products without blowing up the LDPC property as well. So if I kind of assemble all of these things together, what the scheme essentially does is it starts off with some set of logical representatives and then branches out the ones which you want to measure, and then introduces either single expander graphs for the single logical qubit measurements or adapters to measure products. And in total, you can work out that this gives me the scaling that I've given here, which up to polylog factors is linear in both the number of logical qubits I want to measure and the weights of the representatives for these logical Pauli's, and is all done in O of D time, so the same as kind of traditional lattice surgery. So I mentioned this kind of disjointness condition earlier, and you can actually boost the scheme to measure arbitrary commuting sets of Pauli products using twist-free surgery. And you can use that in order to prepare any stabilizer state in O of D rounds on any LDPC code. This requires a handful of new logical ancilla as well. But yeah, you can then do some other things with this scheme. So for example, you can inject many magic states into an LDPC code at once. And there's some recent work on this kind of direction. And you can also kind of generically just perform arbitrary Pauli-based computation in a parallel fashion, assuming that you're given access to magic states. So there's some kind of fairly immediate questions one might have from this. The first is, at what block lengths does this actually become practical? And this depends on a lot of things, and so that's kind of left for future work. Certainly, we don't anticipate that this is practical for, say, the gross code. Secondly, how one might decode using such a scheme where you're kind of branching and then measuring. And then I mentioned earlier that aspects of this can be combined with fixed connectivity. So working out whether you can actually make a full scheme kind of based on these ideas using fixed connectivity is kind of an open problem. And these two are kind of tightly coupled together. So one would really like to avoid branching, basically, because the asymptotic scaling is fine, but the constant overheads are pretty prohibitive. And the problem is that if you don't branch, then you need to either lose your LDPC property or have some more complicated ancilla system for measurement, which is not just expander graphs. And essentially, you need to go to hypergraphs in order to measure in parallel without branching on high rate codes. And these become more complicated, and fewer guarantees are kind of readily available in the literature. But there may be ways of doing this for sorts of LDPC codes of practical size, which are just kind of numerically verifiable, even if they don't come with these provable guarantees. And I think that's a pretty interesting direction for the near term. And secondly, kind of all of these schemes overall use D rounds of syndrome measurement in order to ascertain the correct logical measurement outcomes with high fault distance. And it would be very nice to be able to lower this time cost to sort of single shot or something in that region kind of surgery. And happily, I can say that we have some work which should be on the archive at some point in the not too distant future on this subject. And these two things are actually very tightly coupled together, because reducing the time cost essentially entails measuring different representatives of the same logical operator simultaneously. Okay, thank you very much. That's me done.
Yeah, thanks for the talk. So this might be kind of a naive question, but I noticed some similarities with the two C computing schemes. So could you possibly give some comments on the similarities and differences?
Hello, can you hear me?
Yeah,
Sorry, I didn't quite hear the similarities between what two things?
the two-dimensional MBQC, the measurement-based quantum computer.
Um, so certainly, if you were to take the scheme which we have here and then foliate it rather than do it in a circuit-based model, then you can still construct kind of the right expander graph as a sort of deformed foliated like space-time volume, which will then measure the appropriate logicals in kind of the same way. If you have a foliated MBQC code, and you can study this using there's a few different ways of looking at it, but using stuff like fault complexes and so on would be like a reasonable way to look at it. As for whether the 2D MBQC model in particular is related to like LDPC surgery, I don't particularly think so, because the kind of concept is that it works on any stabilizer code, and even if you were to restrict specifically to just CSS codes, these are kind of homological rather than topological. So you could have some code which, for example, a good LDPC code, which is certainly does not it does not fit in a 2D system with a reasonable definition of fitting.
Okay, I think that's fine. Thank you.
So my question's about the fault distance. So I think I might have missed it, but I think you mentioned in one of your earlier slides that the fault distance is preserved. So does that mean the fault distance just equal to the code distance? Is that what that means?
Yeah, so to be more specific, working in the phenomenological model where data qubits and check qubits can experience errors on each round of syndrome measurement, the fault distance in that noise model of the protocols is always at least as high as the distance of the original codes. So if you imagine like the code in the idling operation for D rounds, and then compare it to the surgery operations that we're doing, the fault distance in the phenomenological model is the same between them, or I would say at least as high, actually, because it's possible to make it higher.
What about then if you use like circuit level?
Yeah, so this is going to depend kind of to an enormous extent on what the syndrome extraction circuits you construct are for the Ancilla system. So there are some things that you know about this a priori without specifying the original codes that you have in mind or the specific expander graphs, because you know that you're making an expander graph and you know that the construction of the branching is kind of this hypergraph product, and so some of the syndrome extraction circuits you can infer from what the syndrome extraction circuits are in the original code. But to a large extent, this kind of has to just be done on a case-by-case basis, depending on what the Ancilla system looks like. I mean, we guarantee that the LDPC property is preserved, but this is just like an upper bound on the check weights and overlaps asymptotically. So it doesn't necessarily mean that the syndrome extraction circuits are going to be close in depth to the depths of the syndrome extractions in the original code, just that, you know, they will have constant depth for some constant.
Right. Okay. Thanks.